So electric charge. Have you ever walked across a carpet in stocking feet and reached for the doorknob only to be zapped by an unexpected shock? Why does your hair mysteriously stand on end when you pull off a wool hat on a winter day? These events are actually caused by the same thing, charges. To understand what is happening, we need to look at the tiny particles that make up atoms of the rug, the hat, the socks, and us. You read in chapter 6 that these small particles are called protons, electrons, and neutrons. So this should all be review for us at this point. Atomic structure and electric charge. Figure 1 is an atomic model of lithium. Recall that neutrons and protons are located in the nucleus, or the center, the red part. And electrons move around the space surrounding the nucleus and can move from atom to atom. That's all that bonding stuff we did. Each element has a different number of protons, neutrons, and electrons. For example, lithium has 3 protons, 4 neutrons, and 3 electrons. Protons repel or push each other away. Electrons also repel each other. Protons and electrons attract each other. This force of attraction or repulsion is known as the electric force. Objects that exert an electric force are said to have an electric charge. Protons have a positive electric charge. Electrons have a negative electric charge. Neutrons do not have any electric charge. Table 1. We've seen table 1 before. Okay, so here's an important point. When there is an equal number of protons and electrons in an atom, the number of positive and negative charges is equal. The charges balance each other out. The atom is neither positive nor negative. It is neutral. All right, charged and neutral. Objects are made up of billions and billions of atoms, even more than that. Whether an object has a charge depends on the charge of the atom. The outer electrons of some atoms can move from one atom to another. When atoms gain electrons, they become negatively charged. When atoms lose electrons, they become positively charged. When atoms become charged, the object becomes charged. Figure 2a shows a neutral object. So if you're looking here at 2a, it's saying it's neutral because there's the same number of red positives as blue negatives. So they'll sort of cancel each other out. There's no charge. So figure 2a shows a neutral charge that has an equal number of protons and electrons. An object that has more electrons than neutrons is negatively charged. An object that has fewer protons is positively charged. So figure 2c looks pretty obvious here. There's a whole bunch of red charges. So that means this has an overall charge of plus. And we could figure it out. Just figure out how many negatives there are and how many positives there are. And if there were 5 more positives, it would have a charge of positive 5. And so it looks like the middle one here is negatively charged because it has more blue negatives. So this whole idea here is the idea at the center of our lesson. So the law of electric charges is, and this is really, again, our fundamental idea. It's going to introduce it here. So it's all about objects attracting and repelling. And it's all based on this positive and negative charge stuff. So the law of electric charges. Charged objects exert forces on each other. In the 1700s, scientists tested charged objects with many different materials. They observed that the force may be attractive or repulsive. They generalized their observations in the law of electric charges, which states the following. So there's a couple of fundamental points here we need to pay attention to. Objects that have opposite charges attract each other. So negative attracts positive and positive attracts negative. So opposites attract. And objects that have the same charge repel each other. Negatives repel negatives and positive repel positives. There it is. The strength of the force between charged objects is related to the distance between objects and the amount of charge on each object. The electric force decreases as distance between the objects increases. The electric force increases as charge increases. So the closer they come together, the more they're going to repel each other. You know, it's kind of like taking two, what do you call it, magnets. You know, there's a positive and a negative end to a magnet. So if you put the negative ends together, put them closer together, they're going to start to repel. Yeah, that's pretty much it for that. So let's get some paper out, or typing, or whatever we do. Hey, where'd my lesson go? Let me just grab the lesson here. I had it out, I must have closed it. All right. Okay, anytime here. Here we go. So this is section 12.1. Electric charge. All right, so there's our fundamental idea here, that all atoms have both positive and negative particles, protons and electrons. We're not really concerned about neutrons today. So I want to do a little, I guess it's math on the next couple of slides here with these positive and negatives. It's really just about counting the charges, though. Okay, so neutral objects have the same number of pluses and minuses, so you can write that. And then I just put this, what's supposed to be a bar. It's an amazing bar, I know. And it's got some plus charges and some negatives. Maybe I should have made them different colors. So you can see we have a couple of positives and a couple of negatives. So the point is, two positives and two negatives, they cancel each other out, and there's no overall charge here. Okay, so that would be a neutral example, and that's where all atoms start. In theory, they all start as neutrally charged objects. By the way, in your later quizzes, there's going to be some pictures, and you're going to have to do some counting, so there'll be some similar questions. All right, so here's an example where we have more positives than negatives. So, I don't know, I guess there's a couple of ways you can look at this. You can do the math there, that's fine. Another way to say is, okay, every one positive is going to cancel out with one negative. So literally, we have a charge plus 2. There's two pluses that aren't canceled out. However you want to think of it. Ugh. All right, a couple more seconds here. If we've done neutral and we've done positive, probably safe to assume the next slide is going to be our negative charges. And you're right. So that one negative cancels with that positive. Got an overall charge of -2. Again, however you want to represent this is your business. All right, a couple more seconds here. Again, hopefully you guys are getting this down, not only for a quiz later, We do have an exam at the end of this course. You might want to have some notes and some knowledge and some memory of what we did. Okay, so a couple points here about electric charge. So objects are only able to lose or gain electrons. We've talked about that. And electric force. I just wanted to include that definition of what it is. So electric force is a force of attraction between two objects. I don't usually, when I'm talking about the lesson per se, I don't really talk about electric force. I just say things are attracting or repelling. But again, going over some of our future questions on the quiz, there were some things that kind of talked about electric force. So I thought I'd throw that definition in. Sorry. All right, another 30 seconds here. Hopefully that's enough time to get these down. Alrighty. Okay, so a couple things left here. Just want to go about those law of electric charges. So it might be beneficial to draw the pictures that go with these. So the law of electric charges, opposites attract. I'm trying to indicate that these things are going towards each other. If you want to add some arrows in. I guess these are supposed to be balls on a string that are charged. A pith ball, they're called. If you're thinking about an atom, you know, it's got those protons in the middle that are positive, and perhaps they're keeping those negative electrons from flying away because of the opposite charges attract idea. Okay, so opposite charges attract, and that means that like charges repel. So again, you might want to include some arrows, these things flying apart from each other. I don't know. It's probably pretty good. There is a third situation here, too. Ten more seconds here. Okay, our third situation is a charged object, whether it's positive or negative, will actually be attracted to a neutral object. So we hadn't really talked about neutral here. And we got a balloon sticking on the wall. The wall is neutral. You charge the balloon by rubbing it on your head, and it becomes charged, and then it's actually attracted. We're going to discuss this idea a little more tomorrow, actually. So we got something to look forward to. So that's the last note there. If you want to go grab section 12.2 off the website, we'll look at that next. All right, let's go find that. Okay, here is 12.2. You can obviously see we got a quiz coming up underneath. A nice picture there, lots of positives and negatives. This section is actually about lightning, part of it anyway, which is kind of interesting on itself, on its own. This section is really kind of at the heart of this whole unit, and it's static electricity. So there's kind of two kinds of electricity, if you will. There's static electricity that is just, it's like a charge that builds up and it can kind of go anywhere it wants. That's what lightning is. We've also got the idea, and we're going to tackle it in next chapter, is current electricity. You know, when you plug something in, and a current electricity is like a control. It's basically we're controlling the flow of electrons. We've got control over it. You turn them on and off. The static electricity, it's kind of just running wild, and sort of just have to deal with it. So static electricity and discharge. What do lightning and a photocopier have in common? The surprising answer is static electricity. Static electricity is an imbalance of electric charge on the surface of an object. Static means not moving. This form of electricity is called static because the charges stay in one place until they move suddenly from one object to another. Somebody's mic's on there, by the way. The device the girl is touching in figure 1 is called a Van de Graaff generator. It's kind of hard to see, but it's like these two giant silver balls on sticks, kind of, and electricity is essentially passing through her body into her hair. So what happens is her hair ends up being, I guess it's all negatively charged. We just learned in the last section that negatives, a whole bunch of them, are going to repel each other. And so that's why the hair stands up. It's repelling. Anyway, it generates static electric charge. The student's hair in the picture shows what can happen when static electricity builds up on someone touching the generator. Each strand of hair has the same charge. This makes the strands repel one another and spread out as far from one another as possible. So static electricity, buildup of charge. An electric discharge, also known as an electrostatic discharge or ESD, is the sudden movement of static charge between two objects. When you rub your socks across a carpet, electrons from the carpet may move to you. When you touch a metal doorknob, the electrons can move from you to the doorknob. You feel a shock, and you may even see a small spark of discharge. Small electric discharges are not harmful to you, but they can be strong enough to damage delicate computer parts such as hard drives or USB memory sticks. In fact, the microchips and circuitry in small consumer electronics can be damaged by much smaller electric discharges. Lightning. I guess that's why we have surge bars, power bars on your computer. Okay, lightning. A bolt of lightning is an example of a natural electric discharge. It is caused by the difference in charge between a cloud and the ground, between two clouds, or between parts of a cloud. What causes this imbalance of charge? The process is not fully understood, but scientists do have a theory. Swirling winds in a storm cloud causes water and ice particles to come in contact and become charged. Positive charges move to the top of the cloud where ice and snow crystals form. Negatively charged water droplets may move to the bottom of the cloud. If you just take a quick look at the picture here, there's a lot more positives up top, and then there's a lot more negatives at the bottom. And so what they're talking about is as soon as there's like a connection between this cloud and the ground, all these negatives are going to travel towards the ground. And that's lightning. The ground below the cloud develops a positive charge. When the difference in charge between the cloud and the earth becomes great enough, a path forms between the cloud and the ground. When the two parts meet, a surge of electrons travels along this path. This produces a giant flash called lightning. The lightning heats the surrounding air, making it expand very rapidly. This causes the sudden loud sound that we hear as thunder. Use of static electricity. Most of the time we think of static electricity as an annoyance. It makes our hair look messy and can make our clothes stick together. There are, however, many practical uses for static electricity. Static cling film. Advertisers use static cling vinyl film for brightly colored removable signs, decals, and stickers like the one shown in figure 4. The windows of many homes, office buildings, and cars are covered with filters that screen out sunlight. These screens use static electricity to cling to the window. Photocopiers. Go down here. I can't seem to scroll down. Photocopiers. Converted image captured by a scanner into a laser beam. The beam is projected onto a drum or belt, creating, oh, there we go, creating, wait for it, a negatively charged pattern. A positively charged ink called toner is attracted to the negative charges in the image. As negatively charged paper moves past the drum, the toner particles are transferred to the paper, recreating the image. That sounds wonderful. Normally what I like to do in my class is we'll watch some videos on lightning, and I don't have one found yet, but I can do that and post it on the website. But what I actually want you guys to do right now is head on over to the website, and I want to do this quiz on lightning, and I'll show you it just because it's a little different. It's a little different format than some of our other quizzes. This one is a reading quiz, so I must activate it. Again, there's Friday's quiz where we only had 3 people do it, so maybe who's ever here can take care of their business and get that done. That would be wonderful. Any other quizzes you haven't finished? I'm just activating this. So let me show you what this quiz looks like. I believe you guys have a literacy quiz coming up. Literacy test at some point, and this one should help you out because it has it's all reading. So all the answers for this quiz are going to be found in this short reading passage. So read it over, tackle the questions. You know, when you find a question, if you're not sure, go back and look, find the answer. And there's 10 questions. I'll give you 2 attempts at it. So I want you to do rate that, right now, right here, rate that, go do it. Recording stopped.